Well, let's see. Okay, so there are a number of really interesting questions I'd like to ask you about, but just for people listening, because this is for a general audience, I'm going to ask you kind of a straightforward question just to start off and lay some groundwork here. So, can you tell us, like, what is a quantum computer? I've heard it overhyped, people,
Yeah.
underhyping it. Why do we care about this?
Well, a quantum computer is the first kind of computer that's been proposed that would operate on principles that are sort of fundamentally different than the principles that were laid down by Alan Turing, 80 years ago, and that have governed all of the computers that we've had in the world. I mean, everything from a supercomputer to your iPhone to an old-fashioned vacuum tube machine, right?
Yeah.
They all operate on, the same rules, the same rules of, Boolean logic and so forth. They differ in how fast they are and how much memory they have and how many parallel processors they have. But in some fundamental sense, they can all simulate each other. And not only do that, but they can simulate each other in a way that's theoretically efficient. Like a problem that took only linear time, that had only linear scaling of runtime, with the problem size on one type of machine would also have linear scaling on another machine, right? It
Right.
wouldn't have exponential scaling, right, or anything like that. And so, there were certain problems that we think are exponentially hard. That is, any algorithm for them requires exponential scaling. And that's true no matter how computers improve, as long as they're built on the same principles. Okay. A quantum computer is different because it actually exploits something different about the laws of physics, namely quantum mechanics, which, in some sense is, the most surprising thing that was ever discovered about physics, or a candidate for that, almost 100 years ago. And I don't know how much you want me to go into this and how much time we
Sure.
have.
No. Yeah. Well,
Yeah.
well, why do you say quantum mechanics is perhaps the most interesting thing discovered about physics?
Because it's not changing this or that detail of, like, what is the world made of, or like what are the particles like, or how do they move around. It's changing the way that you have to calculate the probability that something happens, right? So it's sort of it's at a level, it's changing a level of reality that you might have thought was not even physics, that was just pure math,
Yeah.
right? That was, I like to call it an operating system that the rest of physics runs on as application programs, right? It's barely even physics, right? So the canonical quantum experiment is the one where you shoot photons one at a time at a screen with two slits in it. And then you look at where the photon ends up on a second screen behind it. And what you find is that there are certain places where the photon never likes to appear. Okay, now, by itself, that, wouldn't be such a big deal. You could, make up all kinds of, theories that could explain that. And when you rerun the experiment with the same initial conditions, then the photon can land in a different place each time. So nature is probabilistic. And people make a huge deal about that. Einstein didn't like that God plays dice and blah blah blah. But that by itself is also not the big deal, right? If that was all that there was to it, then we could imagine that each photon has a tiny little ID tag that we simply can't see, and that somehow secretly determines, am I a photon that will go left, or am I one that will go right, right? But here is the part that is really the staggering one, I think, that so we had these two slits, right? Now, if I close one of the slits, then the places where the photon previously could not appear, now it can appear in those places. Okay,
Hmm.
so in other words, by decreasing the number of paths that a particle can take to get somewhere, I can increase the chance that it gets there. Okay, and so basically, over a few decades, from like 1900 until 1926 or so, physicists found more and more phenomena that were like that, that they could not explain, until finally they came up with this mathematical framework that made some kind of sense of all of it. And what that framework says is that for each possible way that the world could evolve, or let's say for each possible path that a photon could take, each slit that it could pass through, you don't only have to assign a probability that it will do that, right? I mean, we use probabilities all the time, even before quantum mechanics, right? You might say, there's a 30% chance of rain, a 30% chance that a particle will go this way. You would never say a negative 30% chance, though, right? That would just be nonsense.
Right.
Okay, but what quantum mechanics says is that each possible path actually gets a number called an amplitude, which can be positive or negative. In fact, it can even be a complex number. Okay, and now the rule is that if you want to know the probability that something will happen, well, you take the squared absolute value of its amplitude. Okay, so something that has an amplitude of 0 will never happen, right? And now, crucially, the amplitude for something to happen is the sum of the amplitudes for all of the different ways that it could have happened. Okay, and so, for example, the explanation for this two-slit behavior is that if the photon can reach a certain spot by taking one path with a positive amplitude, but another path with a negative amplitude, then those two contributions can interfere destructively and cancel each other out. So that the total amplitude is 0, and then that thing never happens, right? If I close one of the slits, then the amplitude is positive or negative, and so now the thing can happen. Okay, now this is kind of the one trick of quantum mechanics, right? Everything else you've ever heard about the weirdness of the quantum world is this thing, this replacement of probabilities by these complex numbers, these amplitudes, but just repeated over and over again. Okay, and in particular, a quantum computer would be sort of a massive application of this sort of amplitude behavior of nature. So now a key point about these amplitudes that was recognized from the very beginning, from like Schrodinger's paper in 1926, is that if I have a bunch of particles, like let's say 100 of them, and they can interact with each other, then it's not enough to write down, say, the amplitudes for the first particle to be in all the possible places that it could be, the amplitudes for the second particle to be in all the possible places, and so on. No, you need to write down the amplitudes for all of the combined ways that all of the particles could be. Okay, so to understand what that means, imagine that we had 1,000 particles that could each be in one of two states. You could call them spin up or spin down. Okay, which is just some property of a particle that you can see when you look at it.
Sure.
In quantum computing, we prefer to call that a quantum bit or a qubit. That is, like a bit that can be 0, 1, or it can have some amplitude for being 0 and some amplitude for being 1, which we would call a superposition of the 0 and 1 states. Okay, now the key point is that if I have, let's say, 1,000 of these quantum bits, these qubits, now I need an amplitude for all 2 to the 1,000th power possible configurations of all 1,000 bits. Okay, there's an amplitude for all of them to be 0. There's an amplitude for them to be 0, 1, 0, 1, 0, 1, and so forth. There's an amplitude for them to spell out a line of Shakespeare. Okay, and so on. So with just 1,000 particles, that's already more amplitudes than you could write down in the entire observable universe. Okay, and yet if you can get them to interfere with each other, in the quantum mechanical way, then somehow they all contribute to, affecting the probabilities of which outcomes you do see when you look at your particles. Okay, and so chemists and physicists actually knew about this exponentiality for a long time. They knew about it mostly as a practical problem, right? If you're trying to simulate quantum mechanics with a conventional computer, for example, to learn about the rate of some chemical reaction or something like that, right? This exponential blow up is a problem, right? The size of the what's called the wave function, right, or the list of amplitudes that you've got to keep track of, could double or more than double with each additional particle that you add. Okay, and so outside of some special cases, it becomes just intractable to understand what complicated molecules are doing. And you can only try to get a toehold with some of the biggest supercomputers that now exist. Okay, so it was in the early 80s that a few physicists, most famously Richard Feynman and David Deutsch, had the idea, well, if nature is giving us this computational lemon, then why don't we make lemonade out of it, right? So why don't we build a computer that itself would be made of qubits, that itself would have an exponential number of these amplitudes that could interfere with each other. Of course, they then face the question, well, supposing that you built such a computer, which they call a quantum computer, what would it be good for? And at that time, they really only had one answer to that question, which was it would be good for simulating quantum mechanics itself, right? Yeah. That is, by the way, still by far the most important application of quantum computers, I think, if and when they become truly practical. There's an enormous number of engineering problems, material science, condensed matter physics, and so on, where if you had a universal programmable simulator for quantum mechanics, that would really help. But what really made people interested in quantum computing, what really started it as a field, was a further discovery in the mid-1990s, and this is that if someone built a truly scalable, programmable quantum computer, meaning with millions of qubits, for example, then you could use it to do more than simulate quantum mechanics. You could use it to solve even certain completely classical problems that, as far as we know today, seem to be exponentially hard for classical computers. Now, the most famous example of that is finding the prime factors of enormous numbers. Okay, which, why do we care about that? Well, that happens to be the problem that most of the encryption that currently protects the internet is based on, right?
Right.
Factoring and a few other problems in number theory, which, as it turns out, would also be solvable with a quantum computer.
So does that mean, does that mean then that, because I had mentioned in the email I sent to you, I had done some small, I was basically like a code monkey for this professor and grad student on a D-Wave quantum computer. And the way the professor described it was that these sorts of being able to break encryption, the race to get to quantum supremacy was similar to the race for a nuclear bomb, in that whoever got there first would have this enormous power that...
Sorry, you cut out.
Okay. I was saying that the professor had said that
the race for nuclear energy.
Yeah. Do you feel like that's at all comparable, or is that an exaggeration?
I've certainly used that analogy. That is an analogy that could be made. The similarities are that you have the laws of physics predicting that something is possible. Right, something that involves an exponential growth, by the way, right? In one case of fissioning particles, and in the other case of amplitudes. That prediction seems absurd to some people, but in some sense, if the prediction were wrong, then ironically that would be the more surprising thing, right? Because you're just taking the currently known physics for granted when you make prediction that this is possible. For it to be wrong, something new has to happen in physics. Now, in both cases, um, just because something is possible, tells you nothing about how soon it is going to be achieved, right? And I feel like this is an error that people constantly slip into, right? They think if you say that something is possible, they translate that as it must be possible in a few years. And if explain, it's not going to happen in a few years, then they translate that as it's impossible, right? But, there is a third category. I mean, other analogies that people make here, powered flight. I mean, people realized, that could be possible for hundreds of years before the Wright brothers, right? I mean, classical computing. You had Charles Babbage, more than a century before the invention of the transistor. That really made the idea practical. Now what was striking about the case of nuclear fission was just how fast it happened in that case, right? That Szilard had the idea in 1933, and then the bombs were dropped on Hiroshima and Nagasaki 12 years later, right? And and I think almost no physicists in the 1930s would have predicted that, right? There's a famous story of Niels Bohr where he said, sure, in principle, you could build a fission bomb, but in practice, it will never happen because you would have to convert a whole country into a uranium enrichment factory. Okay, and then, in like 1942 or so, he finally was able to see, he was able to see the Manhattan Project. And he said, well, I see that that's exactly what you've done, right?
Yeah.
So and it's similar with quantum computers, right? People constantly ask me to try to forecast when we'll have useful quantum computers, and I always try to dance around that question and avoid answering it, right? I mean, I read the news these days, and I don't even know how much longer civilization will last for, right?
Yeah.
But there are so many uncertainties, right? But at some point, these things become a question of how badly do people want this? Are they willing to spend like hundreds of billions of dollars to make it happen? Do they have the organization to follow through with that? Right? And when it gets down to that kind of question, it could be 5 years and it could be 50 years.
One of the things when you were talking earlier about the sort of like the weirdness and the counterintuitive aspect of quantum mechanics,
Yeah.
I had talked to Chomsky on this podcast, and he was speaking as a cognitive scientist, where he was saying
Mm-hmm.
that human brains, generally speaking, sort of they're good at understanding determinism, like billiard balls, things hitting one another, and
Mm-hmm.
randomness, things just
Mm-hmm.
throw the dice.
Mm-hmm.
But things like free will and consciousness don't seem to abide by those sorts of principles. Do you think that uh, quantum mechanics can sort of fill the gap in our reasoning there, or is that?
Well, there have been speculations about that, since like before the ink was dry on, Schrodinger's paper, right? People have been talking about, could quantum mechanics help to explain consciousness or free will or whatever, since there was quantum mechanics. There are a few problems that sort of, those are such enormous mysteries, and quantum mechanics is such an enormous thing that we know about the architecture of the world that I don't dismiss the possibility that they have something to do with each other, right? I don't, okay? But having said that, any attempt to relate them, has some very huge obstacles to overcome, that I think people ought to be better aware of, right? The first, obstacle is that, quantum mechanics is, you could say, in a broad sense, is still a mechanistic theory, right? Like in the sense that if you know the initial state of a system, of a quantum system, and if you know the laws governing the evolution, then you know completely how this list of amplitudes is going to evolve. And that means that you can exactly predict, not necessarily the outcome of the experiment, but you could predict the probability distribution over the possible outcomes. Okay, so you could say the only thing that is left for free will to do, if the initial state were entirely known, and if the evolution were entirely known, then the only thing that would be left would be like one spin of a roulette wheel, right?
Mhm.
Just to select an outcome from this probability distribution, right? I mean, like think about radioactive atoms, right? Each one has a half-life, which means we don't know exactly when it will decay. We know exactly what is the probability distribution over decay times, right? So if you have a whole sample of uranium atoms or whatever, then you know almost exactly what fraction of them will have decayed by such and such a time, right? Now, would we say that each individual uranium atom has free will? I mean, that would just seem like a strange use of language, right?
Yeah.
And so then, you could say, well, if that would be strange for the uranium atom, then one has to articulate then how is the brain different from that, right? Now I have a long essay that I wrote 7 years ago called "The Ghost in the Quantum Turing Machine," where I try to sketch out a view where quantum mechanics is important to these questions, but what's really important about it is not just the randomness. What's important is sort of the unknowability of the initial state, right? So a further property of quantum mechanics, and this is not something that is shared by just classical randomness, okay, is the property that you cannot exactly learn the state of a system, even just an atom, without um, um, inalterably changing the state. Okay, you're measuring the state, forces it to make up its mind, to sort of collapse, to sort of lose its superposition character. It's no longer this list of amplitudes. Now it's just peak at one outcome because you caused this atom to interact with its environment, with the larger world. Um, and so, you could say, so one question that people have debated for a long time in the philosophy of mind, is the question: could you make a perfect replica of a person? Or let's say, would you agree to have yourself teleported to Mars, by a machine that would just scan your brain, email all of the information to Mars, and then a perfect copy of you would be reconstituted on Mars, and then let's say the original copy would be painlessly euthanized, right? Would you agree to that, right? I mean, if it's a perfect, on the one hand, it's a perfect copy, so it seems like it should be no different from just getting on a bus and or getting on a spaceship and going somewhere. On the other hand, I think I'm not alone in feeling unease, right, about that procedure. Uh, and what quantum mechanics actually suggests is that depending on how much of the microscopic detail of a person's brain you would really have to capture to make a good enough copy of it. It might or might not be possible in principle to actually do what I just said, to transcribe the state of a brain as information. It might require making measurements that would just necessarily alter that brain. Okay, so you could, in physical systems in quantum mechanics have a sort of privacy to them, that they don't have in classical physics. Now it's not obvious that has anything to do with these mysteries, because it could be, for example, that you can perfectly well predict someone's behavior in practice by just scanning the more macroscopic parts of their brain, like how are the neurons wired together? Are they firing or not firing? And that in the far future, some nanorobots could do that, without doing much damage to the brain at all, right? That's possible, but quantum mechanics opens up the possibility that there could be a limit there, a limit to copyability coming from physics. So I did try to explore what that means. Maybe I should add none of this really touches on, the hard problem of consciousness, right? The problem of like, why does it feel like anything to be a brain, right? Why aren't we just, complicated computers made of meat? Or alternatively, could it feel like something to be a computer program? And those are questions that I think of as like vertiginous, like questions that it's not clear how any reasoning or any empirical science ever gets a toehold on those sorts of questions, and it doesn't even seem to matter much if the world is classical or quantum. Like you could say, why should some people say, oh, well, if the brain is quantum, then that would somehow explain consciousness. But why, right? Why would a quantum mechanical brain, feel like anything, to be any more than a classical brain?
Yeah, and that kind of that leads into a post I had seen you had written about integrated information theory, which sort of purports
Okay,
to explain,
sure.
uh, be able to calculate consciousness in any physical system. And you made a good
Mm-hmm.
point where you're like, okay, any scientific theory you could invent to explain consciousness still doesn't account for the fact that I could imagine some zombie that has all those physical characteristics and yet doesn't feel the same feeling of consciousness that we do.
Mm-hmm.
Um,
That's right.
so
That's
yeah,
right. I mean,
yeah,
I wasn't saying anything original there. I mean, Chalmers and and hundreds of philosophers before him have made the same point, right? But I mean, with regard to integrated information theory, I was making a much more specific point, in
right.
that post, right? I was saying, so that is a proposed theory that tries to, if not explain consciousness, then at least tell you how much consciousness is present in any physical system, or be able to tell you, is a given system conscious or not, just as a function of how it's organized. And the argument that I was making in the post that you mentioned is that integrated information theory just manifestly fails even at that limited task, right? And the way I argued that was by reductio ad absurdum, right, or by counterexample. Okay, I constructed examples of systems that seem to me plainly not conscious, or rather, if they are conscious, then so is a bag of potato chips, and so is absolutely anything,
But
right?
they would
That we
claim that
know
it
of
is
life.
though.
What?
So I talked to Christoph Koch about this, and he
Yeah,
would say
yeah.
that yeah, like a bag of peanuts would be on some level conscious, like a very minimal
Well,
amount.
right, but okay, yeah, but the problem is that according to so if IIT predicted that it was a minimal amount, that would be okay. But we can construct systems that seem, as plainly dumb as a bag of peanuts, but whose integrated information is enormously greater than the human brain's is. Okay, so that is the problem. Okay,
Yeah.
and that is the reason why this integrated information is just not a good measure that sort of captures what I think what anyone meant prior to this theory by words like consciousness, right? I mean, now, Giulio Tononi, who's the founder of IIT, responded to my post, wrote a whole essay about it. His response was just to bite the bullet and say, yeah, if you constructed these systems, is like like a gigantic mess, a grid, just compute some error correcting code or something like that, then yeah, that would have more consciousness than a person, and that might be unpalatable, but that's just what the theory says. So science is not about confirming the obvious. We should just go along with that non-obvious conclusion, right? But I mean, to me, the problem with that just seems staggeringly obvious. Like if you have a theory that has made correct predictions about some things, and you could check them, right? Like, if you had a theory that, could measure the temperature of ice and of boiling water and tell you that the boiling water is hotter, right? Then maybe you trust that theory, even about realms far from your experience, like to tell you about the temperature of the sun. or something like that. Okay, but integrated information theory, in some sense, the only way we have to test it, at present, is does it give the answers that we would hope that it would give for things like the human brain, for the bag of peanuts, for a rabbit, for a frog, for cases where we feel like we have some prior intuition about how much consciousness is there. If it gets those cases wrong, then what is there for it to get right? What
Yeah.
what grounds do we have for believing the theory in the first place?
Um, that's interesting because when I talked to Christoph Koch about it, he said
Yeah.
that because that he would make a difference between artificial and natural systems, and the example you gave of a giant grid of error correcting code
Mm-hmm.
would sort of fall outside of the domain of IIT because it's in
Mm-hmm.
some sense artificial. Do you think that's
That is
a
emphatically not Tononi's position. Okay, so the
right?
founder of IIT emphatically disagrees with that. He says, no, this is a theory for telling you whether an arbitrary physical system is conscious or not. And in some sense, if you had to restrict the scope of the theory and say, well, in those cases where it gives an absurd result, it just doesn't apply to those cases. Well, then, in some sense, what is the point of the theory, right? We
Yeah.
already knew that, we already had the idea that our brains are conscious, that within our brains, let's say the, cerebral cortex, seems to be the seat of consciousness, much more so than, the cerebellum or whatever. We already had the idea that, that a brick wall is not conscious, or that a uniform grid of exclusive OR gates is not conscious. What's wanted is a theory that will explain all of these facts from some deeper principle.
Yeah.
Right. What's wanted is not just a right. Yeah.
No, I mean, I fair enough. I agree.
Yeah.
But
Yeah. 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 Yeah.
the slightly different topic. Well,
Yeah. Yeah.
actually,
Sure.
much different topic.
Yeah.
You, what is your position on like the many worlds theory that there's some parallel universe where we're having this exact same conversation, but maybe you adjusted your glasses a little
Mm-hmm.
differently or something like that.
Yeah.
Do you buy that?
Uh, I think that it is a way of talking about quantum mechanics, and what surprises a lot of people is that it's actually an extremely conservative way of talking about quantum mechanics. Right? People think that it sounds radical and science fictiony, and it was actually bitterly opposed by the sort of founders of quantum mechanics, who basically just had wanted to say, look, there is the microscopic quantum world, and then there is our macroscopic world that obeys classical physics, and you have to draw a line between them somewhere. And what explains why there is that line, or how there could be that line? Well, you're just not supposed to talk about that, right? If you keep asking about that, that just shows that you're mired in the old way of thinking and you don't understand quantum mechanics, right? So I mean, that was a way of that's called the Copenhagen point of view, and there's of course many more words put on it than that, but I think that that's basically what it boils down to. I've called it shut up and calculate, except without shutting up, right? And I think that was guaranteed not to satisfy people forever. People don't just want to know, how do I use this theory to predict the probability that I'll see something. They want to know, what is the world like, or what is the state of the world, what kind of object is it? And and you and me and everyone else, we should just be some patterns, that exist in a state of the world, right? We don't want the laws of physics to be all about us, about what predictions we make. We want it to actually describe a real universe that was here before us and that will continue to be here after we're gone. Now, here's what I would say. I would say, if you believe in what I just said, which is, the philosophers would call realism, right? So if you're a realist about, the state of the physical universe, and also if you think that quantum mechanics is exactly true, so quantum mechanics is not just an approximation to some future theory, but it is literally true. The Schrodinger equation that governs the linear evolution of the amplitudes is an exactly true equation. Secondly, you believe that. And thirdly, you believe that we don't get to add any additional ingredient to quantum mechanics. So we don't get to add a new ingredient that says, that picks out this world as the real world and says that the other world, the world where I adjusted my glasses differently, is just some ghost town where no one experiences anything, right? So with those three assumptions, then I think many worlds is inevitable. Okay,
Okay, so
then that is just where you're led. Okay, so I feel like my personal opinion is exhausted by sort of by clearly laying out what is the decision tree, right? I
yeah.
think you can disagree with many worlds, but then you've got to disagree with one of those three assumptions, either the exact truth of quantum mechanics, or realism, or the completeness of quantum mechanics.
Okay, so I want to understand exactly how the quantum mechanics entails many worlds.
I
Okay,
didn't say that it does.
okay,
I I said that if you want to be a realist about quantum mechanics, and if you want to not add any extra ingredients to quantum mechanics. Okay.
mhm.
So here, but I can explain how how with those assumptions that it entails it. Okay. So the basic idea is, well, we talked before about amplitudes giving rise to probabilities, right? So if I look at a screen to see where the photon landed, then I will see that it landed on a particular spot with probability that goes like the squared absolute value of the amplitude for it to land at that spot. Okay. Now, in some sense, the most mysterious part of quantum mechanics is that very last step. How do the amplitudes become probabilities? Right. So I started out with this superposition, where it was not definitely in any one of the places. It just had an amplitude for being in each place. And then after I looked, then I saw it definitely in one of them, and in each one with an appropriate probability. Okay. So how did that happen? And it seems like it can't possibly be that I looked, right, because or that a conscious being looked, right? Because in fact, it doesn't have to be a conscious being that looked. In the following sense, if the information about where the photon was got recorded in the state of the external environment in any way whatsoever, so like if it leaked into the other radiation in the room, or the air molecules, or the vibrational modes of the screen, if the information about where the photon was has leaked out in any way, then the effect on the photon will be exactly as if the photon had been measured. Okay, so then once you want and you can do experiments where you directly confirm that, right, where you see that when the state of your quantum system becomes entangled with the larger environment, then it is as if that system has been measured. Okay, that's called decoherence. The loss of the coherence of a quantum state. Okay, and this is sort of is now understood to be absolutely central to the story of how quantum mechanics gives rise to the appearance of a classical world, right? Like we never see cats in superpositions of alive and dead states, right? Or we never see balls in superpositions of thrown and not being thrown. Okay, that's not because it's impossible in principle. That's simply because cats and balls are such large objects that are so tightly coupled to their environments that the instant that you tried to put a ball into a superposition of, throwing it and not throwing it, the information about what you had done would have leaked out. Okay, it's kind of like, like imagine, you have some embarrassing secret, and people start posting it on Twitter, right? Once they start tweeting it and retweeting it, then you're never going to get it back in the bag, right? And this is why superpositions are really, really hard to maintain, in anything close to the scale of everyday life. Incidentally, this decoherence is also why it is so hard to build a quantum computer, because then you need to have millions or billions of qubits and keep them almost perfectly isolated from their environment so that they don't lose their coherence. Right? That's really hard. Okay, but once you understand this decoherence, then you can what you can do is you can say, well, let's suppose that I looked at a situation where you are looking at a photon. Okay, you are making a measurement of a quantum state, but now I could decide to treat not only the photon, but you by the rules of quantum mechanics. Okay, after all, you're just a big collection of atoms, right? And each of those atoms should be governed by the same laws of quantum mechanics that govern the particle that you're measuring, right? And when we try to do that, the result that we get, is, I would say, it's as unequivocal as it is weird, right? The result is that, initially we start with a state where you are measuring, let's say, the particle to see whether it, I don't know, was horizontally or vertically polarized or something like that, and you don't know which it is. Now we end, and in fact it was in a superposition of the two states. Okay, and we end with a quantum superposition state where there is some amplitude that the particle is horizontally polarized, and you have perceived it as being horizontally polarized, right? So your measuring device has recorded that, your brain has registered the information, and so on. The information is leaked into the air molecules in the room. And then there is also amplitude on a state where the particle is vertically polarized and where you've perceived it as being vertically polarized, right? And there is nothing in the Schrodinger equation, which is sort of the equation that governs how the amplitudes evolve, that's going to make one of those two branches go away, right? They're both still going to be there forever. Once they've become sort of macroscopically distinct, then in practice, they're never again going to interact with each other. Okay, so they'll be separate, forevermore, or at least until the entire universe reaches its heat death. Okay, and that's not an assumption. That's just a prediction that you get from quantum mechanics. And the reason why you would have to add something extra to this picture is if you believe that is just unacceptable, and physics has to deliver for us one macroscopic world, one world of experience. Well, in that case, you would need to add some extra ingredient that would get rid of one of the outcomes. Okay, and now it is far from impossible that such an extra ingredient will exist, right? And I mean, some views about what it would be would even make empirical predictions that in principle could someday be tested, right? So I don't rule that possibility out. I'm just explaining to you why in some sense many worlds is the minimalist option, ironically.
So the only thing I'm having trouble understanding is the idea that because these, and correct me if I'm misunderstanding this at all.
Yeah.
Because these two possibilities, in this case of me observing a certain, like a photon, have a given amplitude, have like a non-zero probability, or non-zero probability, that they must, in some sense, that probability must, if not in this universe be realized, in some other universe be realized. Is that what you're saying?
Okay. Yeah, okay, what's really crucial here is that it's not a probability; it is an amplitude.
Okay.
Okay, amplitudes are different from probabilities. Amplitudes are complex numbers. Okay, they can be positive or negative. You know, they have a phase to them. And why is that so important? Well, because when we have a superposition, so we have, you know, not just, you know, if all we knew was, right, there's some probability that the photon goes this way, and there's some probability that goes that way, then it is always open to us to just say, really, it went one way or the other, right? Really, there's some way that it went, but it's just our ignorance, you know, that prevents us from saying which way, and we encode our ignorance in this language of probabilities. Okay, with when it's a superposition, when it's amplitudes, uh, you don't have that option. Okay, and why don't you have that option? Well, because we in principle, and for small enough quantum systems, also in practice, we can do an experiment where we bring the two branches together and we cause them to interfere with each other. Okay, so you can, you know, if you have a particle, let's say, that's in an equal superposition of, you know, going through a left slit and going through a right slit. If anyone says, well, really, it went through one slit or the other one, you just don't know which one it went through, and so you're just using this whole fancy language of, you know, superposition to just say that you don't know. You can prove that that person is wrong.
Right.
Okay, you can empirically prove that they're wrong, and the way that you do it is by interfering the two paths. Right? You show that in some sense, you know, the laws, you know, the universe must have known something about both of them. Right? Was somehow keeping track of the state of both of them. Okay, so now you could say that, fine, there's that superposition, but in addition to the superposition, on top of it, you know, there is one possibility that is sort of the real one, the ontologically real one. That is exactly what Bohmian mechanics says, right? So Bohmian mechanics is a third position in, you know, the interpretation of quantum mechanics, different from Copenhagen, also different from many worlds. Okay, Bohmian mechanics says, yes, there is this whole superposition, this whole, including over different versions of us and so on, just like many worlds would say. But then the Bohmians would add to it, but, you know, it is only one of the outcomes that is really experienced, and, you know, or that is sort of ontologically real, and all of the other ones are just ghost towns, right? They're there in the equation, but they're not, you know, but they're somehow not not as real, not as experienced. Okay, but then there's, you know, even the Bohmians, they still have to say that those other branches are there in the equation, because if they didn't say that, then they wouldn't get the right prediction.
Okay, so that's that makes sense, I suppose, because my gut feeling is that it's hard to accept this. I suppose part of that is because it
Yeah,
makes me feel small, you know.
you're completely right that it's hard to accept. You're completely right. And look, you know, I have friends who think that, you know, anyone who disagrees with, you know, the many worlds interpretation just thereby proves their irrationality, and that they can't be taken seriously about anything else. Right? I am like I am very moderate compared to that. Let's say, right?
Yeah.
I think that, you know, these are questions where, you know, it is totally unclear how we're going to resolve them empirically, and, but by construction we have all these different views that lead to exactly the same predictions for all the experiments that we can do. So, you know, it's not surprising that it's going to eventually come down to questions like, what do you think that a scientific theory should do for you, right? Is it supposed to describe an objective state of the whole universe, you know, or is it supposed to only describe your experience? You know, in the latter case, you could certainly reject many worlds, right? That's one way to reject it, just by becoming an instrumentalist about physics, right? I mean, another way to reject it is, look, you could say, it could be that, like every other theory in the history of physics, quantum mechanics will someday be superseded by something else, right?
Yeah.
And, if quantum mechanics were to be superseded, then whatever supersedes it might give a definite criterion for when a superposition collapses, when it resolves into a single state. And, as soon as we had a theory like that, well, then poof, all of the many worlds would be gone, right? All the worlds would be gone except for our world, and some, you could say, some very, very nearby ones, that sort of produce the interference patterns that we see. Um, so, at that point, the question becomes, well, like, how, just how much should we believe in the exact truth of quantum mechanics? But I think when quantum mechanics was first discovered in the 20s, people really had the impression that this was provisional, right? That this could easily be superseded by something else. But by now, it's been around for almost 100 years without, a single change, to the fundamentals since Schrodinger wrote down his equation in 1926. Okay, and by now, we have tested it on, vastly bigger scales than they were able to back then. Right, people can do the double slit experiment, not just with photons or with electrons, but with molecules that have thousands of atoms in them. Okay, so not quite big enough to see with the naked eye, but much bigger things. I mean, there is a serious prospect that in our lifetimes people will be able to create superposition states of, let's say, a virus, or like biological things like that. Okay, so it sort of and a quantum computer, even, you could, maybe even more in some ways, would force on us the question, well, where is the cut? If quantum mechanics can extend all the way up to the scale of a programmable computer that could even have some sophisticated AI program running on it and so forth, well, then why shouldn't it extend all the way up to the scale of our own brains, right? But if it extends to that scale, then how do we get out of the inclusion of many worlds? And there's also just this feature of quantum mechanics that it seems like a very, very rigid theory, because it's really just this generalization of probability. It's this sort of level beneath physics. It seems very, very hard to make the slightest change to quantum mechanics without getting complete nonsense. Okay, and in that way, it is very different from, let's say, general relativity, which, there are lots of ways to modify, or the standard model of, of particle physics, or most other theories in physics. Quantum mechanics just seems very, very hard to change. But maybe someday something will be discovered beyond it. Maybe it's just our lack of imagination. And of course, if something is found beyond quantum mechanics, then the whole question of many worlds would have to be considered anew.
Well, that's what you said in there about testing this idea of many worlds empirically. I mean,
Yeah.
how would you even? I mean, do people know if there are even such a thing as parallel universes at all?
Well, no, no. That's exactly what we're talking about, right? I mean, the issue is, quantum mechanics says that, anytime you have two different possible ways that a system could be, you can have a linear combination of those two ways, a superposition of them, and you can also, do an experiment where you see interference between the two components of that superposition. Okay, at least in principle, maybe not in practice. So when people talk, it is not, I should say, it is totally unclear whether there's any way, even in principle, to test the many worlds interpretation, right? It largely depends on what you even mean by testing something, okay? Because here is the kind of thing that people talk about when they talk about, quote unquote, testing the many worlds interpretation. And then these were like the thoughts that David Deutsch had, 40 years ago or so, that were part of what led him to the idea of a quantum computer in the first place. Okay, so Deutsch said, well, suppose that we could take our entire brains and we could upload them into computers. Okay, so we had, consciousness living in computers. Okay, that's just step one of the experiment. Okay, so suppose that of course there would be a question. Would these computer programs, even if they perfectly simulated us, would they really be conscious? Right? But let's suppose that our language had shifted in such a way that that no one hesitated to regard such things as conscious. Okay, well in that case, Deutsch said, in principle, we could take this program and we could put it onto a quantum computer, and we could create a superposition over two different conscious states. Or let's say, a state of the computer program that corresponds to a person thinking one thought, and a state of the program that corresponds to them thinking another thought. Okay, and then crucially, we could do an interference experiment between those two states, so we could prove that both of them were really there. Okay, and at that point, provided that you accepted that this computer was conscious at all, you would have to accept that yes, this conscious being had been in a superposition of thinking two different thoughts, exactly like the many worlds interpretation said. Mm-hmm. Okay, now what having said that, I hasten to add, that the Copenhagen people, right, have, as you might imagine, have a response to this, right? So they say, yeah, if that experiment could be done, we make exactly the same prediction as the many world people for what you would see. Yeah, sure, you would see the interference pattern between the two different states of the person's mind. But then they would say, well, we just talk about it in a completely different way. We say that quantum mechanics is a personal theory, right? It is relative to the user, right? And so if you from the outside were sort of looking at someone else being manipulated in superposition in this way, then, relative to you, you would say that that person was in a superposition, that they had undergone interference, but for the person who was being manipulated in that way, in each state, they would only have, at most one experience, if indeed they experienced anything at all. Okay, and so no one would ever have to talk about themselves being in a superposition state. Okay, but you could say that if this experiment were done, then whether it proves anything, I think it might well change the way that people talk about these things, right? I mean, because then you could imagine some far future where it was just a commonplace to take intelligent beings and manipulate them in superposition states. And you might imagine that in such a future that the many worlds interpretation would be a lot more popular.
Speaking of which,
yeah.
What are your thoughts on the simulation theory? Do you take that seriously at all?
Well, not really, but not because I have a good reason to think that it's false, just because I don't see what it buys you, right? I mean, to say that the universe is a simulation, running in a different universe, okay, great. And maybe that universe is a simulation running in a still larger universe, and so on infinitely, right? In fact, maybe that entire infinite sequence is a simulation, running in some, infinitely large computer. But in science, we try to do better than just constructing towers of speculations, right? We try to say, if this were true, then how would it affect what we experience? Okay, and what the entire idea of the universe being a simulation, unless you add anything to it, it is empirically sterile, right? It predicts nothing, and it explains nothing. Okay, that is the issue with it.
Yeah, it kind of reminds me of like when people talk about a belief in God. It's like it's not even falsifiable.
That's right. So now, if you add something to that belief, if you say God is smiting my enemies, God will answer my prayers, right? Then those are beliefs that have empirical consequences, right? It matters whether those are true or false. Okay, but you could say if God is just an abstract entity that created the universe and then sat back and did nothing, right? Then that becomes very hard to distinguish from the simulation hypothesis at that point. And exactly the same objections of lack of explanatory power would apply in both cases.
Um, and I've already taken up an hour of your time, so I only have a couple more questions left. But the other sort of pop science thing I wanted to ask you about was like the singularity, where people think that there
Mm.
will be an AI that will be so much more intelligent than all of human intelligence combined that it'll
Yeah,
you know
yeah.
take off like that. Do you how do you feel about that?
I mean, it's certainly not impossible. We don't know anything in the laws of math or physics that would say that the human brain, is the absolute, limit of intelligence that the laws of physics allow. In fact, it would be kind of shocking if it were, right? And just like it took hundreds of years, but eventually, we exceeded human, we built machines that could exceed humans along all sorts of other dimensions, whether that's, strength, running, doing arithmetic, or now, even, recognizing pictures and, translating from one language to another and, doing more and more of what we formerly thought of as intelligence, right? So, particularly if one agrees that the brain itself is a physical system, governed by the laws of physics, then it becomes very, very hard to explain why we could not someday engineer, a different physical system that would display, a much greater degree of intelligence. Okay, so up to that point, I think that the singularity people are absolutely right. Now, do I regard this as like the most pressing issue facing humanity? No. I mean, in fact, like in some sense, I would be thrilled if if we survive long enough that being conquered by AI, it becomes the most pressing threat,
Yeah.
right? Like if only I feel like if only we should last that long, right? If only we should survive the climate change and survive the authoritarianism that seems to be taking over much of the world right now. So but having said that, I mean, I think that if you had asked me 10 or 15 years ago, I would have said, this is just really, really far in the future, right? It is so far in the future that it's not even profitable to, be putting that much effort right now into, thinking about how do we prevent AIs from taking over the world, right? It's like someone analogized it to, thinking about, how do we prevent overpopulation on Mars, right? Like, yes, it might eventually become an issue, but it just, we've got much more immediate issues to worry about, right? And I still think that we have more immediate issues to worry about, but I also think that within the last 10 or 15 years, the possibility of human level AI within our lifetimes has become more real. I mean, the successes of deep learning, in the last decade have been absolutely spectacular. I think, way beyond what many of us predicted was possible and, or would be possible in such a short time, and people try to poo-poo them, but it's like, well, did you predict that, by now, that an AI was going to go from, not being very impressive at Go to just a few months later, destroying the human world champion at Go, right? And then it would do that without any particular knowledge about Go, that it would do that just by playing itself millions of times and teaching itself how to play and sort of ignoring, humanity's like centuries of accumulated knowledge about how to play this game. Like, did you predict that? Did you predict that that there would be this text engine, this GPT-3, right, that can come, I would say, at least with people who don't know what they're looking for, now come very, very close to passing an unrestricted Turing test, right? That can converse with you, that can, write essays, at least as good as like a B or C student, high school student, right? About any topic that you ask it to, and then, have some semblance of coherence, to them. Right? If you didn't predict those things, then you don't get to say after the fact that it wasn't impressive, right? And what's a little bit scary, you could say, is that these improvements have not come from a new theoretical breakthrough, so much as they've come from just throwing more and more hardware, more and more training data, and more computation cycles, with just the same types of algorithms that people already knew about, in the 80s. Okay, and so but now the hardware is obviously going to keep improving, right? Massively, right? I mean, the original Moore's law has basically ended now. Okay, but the number of cores, the number of parallel processors, the amount of memory you have, those are still on an exponential trajectory. And if you look at just the raw numbers, in, let's say, the GPT-3 model, right? There is not as much information there as there is in the human brain. Right now, there's maybe as much as there is in some, very small mammal's brain. Okay, but in 5 years, there will be as much there as there is in the human brain. And so what happens then? My guess would be that these methods are going to hit diminishing returns at some point, and there will be some further deep ideas that are needed to get all the way to human level intelligence. But I mostly just believe that because it would just seem too absurd if it were otherwise, right? And one has to admit that so far we have not yet seen that point of diminishing returns. So far, the deep learning methods just do better and better the more hardware you run them with.
The last thing I wanted to ask you about
Yeah,
is I had heard that you had interned at Bell Labs back in the
yeah,
90s. For
yeah.
people who are listening who don't know, Bell Labs for many years was an incredible fountain of research. And you were there as a teenager. Like, what
Mhm.
was that like?
Yeah, I think that was a transformative experience in my life. I had, been very unhappy in high school. I was lucky enough to be able to go start college early through this program called the Clarkson School in upstate New York. So I was already in college then by the time that I went to Bell Labs. But
Why didn't you like high
to
school?
go
Sorry to
from
interrupt.
I
Typical.
think a lot of
Yeah.
I think a lot of the same reasons that one wouldn't like being in prison.
Fair enough.
Uh, no, there were some great teachers. There were some, great friends, but ultimately, you were in a very artificial environment where, you are forced to, you know, uh, uh, you know,
A bell rings and you go to the next
yeah,
class
yeah,
and
yeah, 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 yeah. You need a hall pass to walk around. There is a great deal of bullying. There was a great deal of boredom, of that one has to put up with. Uh, and um, I knew that I liked programming and I liked math, and was very lucky to sort of get to a place where I could pursue the things that interested me. And then to get from that sort of high school environment to within the space of a year or two to Bell Labs. That was incredible for me. I was there in some of the last years that Bell Labs was really a thriving entity. incredibly sad that it was I guess a casualty of deregulation, and that it doesn't exist in anything like the form that it did anymore. But I spent one summer there working on some statistical software. It had nothing to do with quantum computing, but my boss said, "Oh, you're interested in quantum computing, go read up on it." Sure, that's great. And I spent a month doing that, and then I found out that Lav Grover, who was the discoverer of one of the most famous quantum algorithms called Grover's algorithm, actually worked in the same building at Bell Labs. So I
Wow.
went and I talked to him. I had a bunch of ideas for improving Grover's algorithm, which were complete nonsense. They completely didn't work. But Lav Grover was nice enough to say, "Well, why don't you come back and work for me next summer?" And so I did that, and then I met other students who were also working for Lav, like one of whom had come from Berkeley, which at that point was like the center of the world for research in quantum computing theory. So then I found out what was going on in that area, and I still wasn't sure that if I could make any original contribution to that area. In fact, I spent that whole summer working on a certain problem that I couldn't solve, and that fall was then solved by one of the students from Berkeley. Okay,
Wow.
and so then I said, with just a completely new method, just completely different from anything that I had been thinking about, but just seeing that, like to be beaten, so fair and square, right, or so fairly. I mean, I think it made a really big impression on me. It was like, wow, these people in Berkeley, they really know a lot that I don't know, and I really want to go there to learn whatever it is that they know. And it was I actually started in Berkeley doing AI because it was the AI people who recruited me there. So and again, in a different branch of the quantum multiverse, I'm probably still an AI person. And But within a year, I had sort of fallen in with the quantum computing crowd, which was sort of where my heart had been. And I guess it stayed interesting enough that 20 years later, I'm still there.
That's amazing, though, that you worked on that problem all summer, then someone else solves it, and then you've gone on to do all the great things you've done. I mean, I think it's definitely a beacon of hope to a lot of younger people, especially, I mean, just, uh, yeah, listening to that is
Yeah,
it's inspirational. So
yeah.
let's wrap. Sorry, go ahead.
Yeah, no, I was going to say, if you discover something and it turns out to have been already discovered, I mean, this is a good sign, right? Okay, if it was already something that was already discovered, 10 years ago, well, great. Well, then, maybe next time you'll, discover something that was only discovered 2 years ago, right? And then, maybe you'll only, and then eventually you'll discover something that no one has discovered yet, right? So, yeah, and certainly if someone else solves a problem that you can't solve, right, there is an opportunity to learn
All right, let's wrap this up.
something.
Scott,
Yeah,
thank you very much for talking.
sure,
I
absolutely.
really enjoyed this. You're
Yeah,
welcome
yeah,
back
it's a pleasure.
anytime. And
It's a pleasure.
is there anything you want to plug before you head out?
Yeah, no.
Okay.
Okay.
uh, all right, great. Thank you very
All
much.
right.
Take care.
Sure. All right. Take care, Duncan. Okay, bye.
Bye bye.